Imagine a future fueled by the very process that powers the stars. A future where energy is abundant, clean, and safe. This is the promise of nuclear fusion, a revolutionary technology with the potential to transform our world. Fusion involves fusing atomic nuclei together, releasing colossal amounts of energy in the process. Unlike its cousin, nuclear fission, which splits atoms apart, fusion offers a clean and virtually limitless source of power. For decades, scientists have understood its potential, and the quest to harness this power has been long and challenging. But recent breakthroughs in fusion research have brought us closer than ever to this reality. With renewed interest and investment from both governments and private companies, the dream of fusion energy is closer than it has ever been. Fusion reactors produce no greenhouse gases, making them an environmentally friendly energy source. And unlike fission reactors, fusion reactions produce no long-lived radioactive waste, mitigating the risks associated with nuclear waste disposal. The quest for fusion is a journey worth taking, one that could illuminate our world for generations to come. Nuclear fusion and nuclear fission are two distinct processes with vastly different implications for energy production. Fission, the process currently used in nuclear power plants, involves splitting heavy atomic nuclei, such as uranium or plutonium, into lighter elements. This splitting releases energy, but it also generates radioactive byproducts that pose significant environmental and security concerns. Fusion, on the other hand, involves fusing light atomic nuclei, such as isotopes of hydrogen, deuterium and tritium, to form heavier elements, primarily helium. This process, which mimics the reactions that power the sun and stars, releases immense amounts of energy, far greater than fission. Crucially, fusion does not produce long-lived radioactive waste. The byproducts are primarily helium, an inert gas, and neutrons, which can be easily absorbed and managed. Unlike fission, which can lead to runaway chain reactions, fusion reactions are difficult to sustain and control. Fusion reactors are inherently self-limiting, meaning that any malfunction would lead to a rapid cooling of the plasma, effectively shutting down the reaction. In essence, fusion offers a cleaner, safer, and more sustainable alternative to fission. The pursuit of fusion energy is often described as the search for the holy grail of energy production. Fusion offers clean, safe, and virtually limitless power. It doesn't produce greenhouse gases or harmful pollutants. Fusion reactions are inherently safe and can't run out of control. In a world facing an energy crisis, fusion is a beacon of hope. Fusion combines light atomic nuclei, releasing tremendous energy. This powers the sun and stars, sustaining life on Earth. On Earth, fusion involves hydrogen isotopes, deuterium, and tritium. Under extreme conditions, their nuclei fuse, creating helium and a high-energy neutron. Energy release is governed by Einstein's E+mc2. Section 5. Extreme conditions, creating a star on Earth. Fusion requires recreating the extreme conditions of stars, millions of degrees Celsius, and immense pressures. Achieving these on Earth is a major challenge. Temperatures over 100 million degrees Celsius are needed to overcome nuclear repulsion. At these temperatures, matter becomes plasma, a sea of charged particles. High pressure is also crucial for fusion. It forces nuclei closer, increasing fusion chances. Confinement is another significant challenge. Plasma must be confined long enough for sustained reactions. Two main approaches: magnetic and inertial confinement fusion. Section 6. From hydrogen to helium, the products of fusion. The fusion of deuterium and tritium, the isotopes of hydrogen, is the most promising reaction for achieving practical fusion energy on Earth. This reaction produces two primary products: helium and a high-energy neutron. The helium produced, specifically helium-4, is a stable and non-reactive element. It poses no environmental threats and is commonly used in various applications, from balloons to medical imaging. The production of helium as a byproduct of fusion is considered a positive aspect, as it is a valuable resource with numerous industrial uses. The high-energy neutron, however, is where the true energy payoff of fusion lies. This neutron carries away the majority of the energy released in the fusion reaction. Harnessing this energy is crucial for making fusion a viable energy source. The energy of the neutron can be captured and converted into heat using a surrounding blanket of material in the fusion reactor. This heat can then be used to generate steam, which drives turbines to produce electricity, much like in conventional power plants. The process is clean, efficient, and produces no greenhouse gases. Section 7. Taming the Beast, Magnetic Confinement Fusion. One of the leading approaches to achieving fusion energy is magnetic confinement fusion, or MCF. This method uses powerful magnetic fields to confine the superheated plasma, preventing it from contacting the reactor walls and allowing fusion reactions to occur. The most advanced MCF device is the tokamak, a donut-shaped reactor where magnetic field lines twist and turn toroidally like a donut to confine the plasma. The ITER project, an international collaboration currently under construction in France, is the world's largest tokamak and aims to demonstrate the feasibility of fusion power. Another MCF concept is the stellarator, which utilizes a more complex, twisted magnetic field configuration to confine the plasma. MCF research has made significant strides in recent years, with advancements in superconducting magnets, plasma heating technologies, and computer simulations. These advancements have led to higher plasma temperatures, pressures, and confinement times, bringing us closer to the elusive goal of ignition, the point where the fusion reaction becomes self-sustaining. Section 8. A burst of energy inertial confinement fusion. Inertial confinement fusion, or ICF, is an alternative approach to achieving fusion that uses lasers or particle beams to compress and heat a small target containing fusion fuel, typically a tiny capsule filled with deuterium and tritium. The National Ignition Facility, or NIF in the United States, is the world's largest and most energetic ICF device. NIF uses 192 powerful laser beams to deliver a precisely timed pulse of energy onto a target the size of a peppercorn, creating conditions similar to those found in the core of stars. In ICF, the inertia of the imploding target confines the fuel for a short period, long enough for fusion reactions to occur. This approach is akin to creating miniature stars that burn brightly for a fraction of a second, releasing a burst of fusion energy. Section 9. Alternative approaches, exploring new frontiers. While magnetic confinement fusion and inertial confinement fusion are the most established approaches to fusion energy, several alternative concepts are also being explored, often driven by private sector innovation. One such concept is magnetized target fusion, which combines aspects of both magnetic and inertial confinement. Magnetized target fusion uses magnetic fields to confine a plasma target that is then compressed using lasers or pistons, creating the conditions for fusion. Another promising avenue is the Z-pinch, which uses a powerful electrical current to pinch and heat a plasma column, generating fusion reactions. Private companies are playing an increasingly important role in advancing fusion research, often taking unconventional approaches and leveraging advancements in areas like high-power computing, materials science, and artificial intelligence. This influx of private investment and innovation is injecting new energy and urgency into the quest for fusion power. Section 10. The Fusion Frontier. Current projects and challenges. The pursuit of fusion energy is a global endeavor, with numerous research projects underway worldwide, each pushing the boundaries of science and engineering. The International Thermonuclear Experimental Reactor, currently under construction in France, is the world's largest and most ambitious fusion project. ITER aims to demonstrate the feasibility of fusion power by producing 10 times more energy than it consumes, paving the way for future commercial fusion power plants. In the United States, the National Ignition Facility continues to make strides in inertial confinement fusion, pushing the boundaries of laser technology and fusion energy output. Meanwhile, private companies like Commonwealth Fusion Systems and Helion Energy are developing innovative approaches to magnetic confinement fusion, with the goal of achieving commercialization within the next decade. Despite the remarkable progress in fusion research, significant challenges remain. Achieving ignition, the point where the fusion reaction becomes self-sustaining, is a major hurdle. Maintaining stable plasma confinement, developing materials that can withstand the extreme conditions inside fusion reactors, and achieving efficient energy extraction are also critical challenges. Section 11. A brighter future. The potential of fusion energy. The successful development of fusion energy holds the potential to transform our world, addressing some of the most pressing challenges facing humanity, from climate change to energy security. Fusion power plants would have a minimal environmental impact, producing no greenhouse gases or long-lived radioactive waste. They would be inherently safe, with no risk of meltdowns or nuclear proliferation. And with the fuel for fusion readily available in seawater, fusion offers a virtually limitless energy source, ensuring energy security for generations to come. The benefits of fusion extend beyond electricity generation. Fusion neutrons can be used to produce valuable medical isotopes for diagnosing and treating diseases, offering new tools for healthcare. The timeline for commercial fusion energy remains uncertain, but the rapid pace of technological advancements suggests that the dream of fusion power is closer than ever before. Section 12. The future is fusion, a call to action. The quest for fusion energy is a journey that demands our attention, our support, and our active participation. Staying informed about the latest advancements in fusion research is crucial. Engaging with policymakers, supporting research initiatives, and advocating for clean energy solutions are all ways to contribute to the realization of fusion power. The challenges in achieving practical fusion are significant, but the potential rewards are too great to ignore. By working together, supporting scientific innovation and demanding a clean energy future, we can make fusion a reality and unlock a brighter future for all.